Welcome back. I'm still Ron Daniels, and I'm still the Science Entrepreneurship Coordinator. Looks like we're ready for the second part of the CAD lesson. The purpose of this lesson is to teach you a bit about how the CAD works so that when you try to use it, you won't get too frustrated and or stuck. Some of the problems you might run into aren't really intuitively obvious, but luckily, once you understand the underlying concepts, SolidWorks becomes very natural and intuitive to use. The first concept that we need to talk about is what we call normalcy. We usually start off this section of the training by asking the student, "Psst, hey, do you know what normal is?" Which generally just confuses them. So we explain that we're talking about normal in the geometric sense, as in a line or a vector being normal to a plane. Almost all of you will tell us that you don't remember what normal is, but almost all of you actually do remember with a little bit of prompting. So if I show you this pen coming up from the plane of a piece of paper and it's coming up like this, you're going to tell me that it's not normal. And if I go like this, you're going to tell me that it's not normal. But if I go like this, where the pen is sticking straight up from the paper and it doesn't matter what direction I measure from, it's always 90-degree angle, you will tell me that it is normal to the paper, thus proving that you lied to me when you said that you didn't know what normal meant. We remind you of this concept because it's very important in the CAD and it will come up again and again. So we like to bring it up to the top of your mind right here at the beginning of the lesson. It also helps for us to demystify the CAD jargon so that we're not sitting here thinking, yeah, the student knows what that means, while the student's sitting there thinking, I have no clue what that means, but I'm embarrassed to admit it, so I won't ask. The next thing that you're going to lie to us about is something called extrusion. When we ask you, you'll all say that you don't know what it is and that you've never done it. And I will reply by saying this. So in fact, extrusion is done in most households at least once a day and preferably again before bed. When I squeeze the toothpaste out here, I'm extruding the toothpaste. So in real life, extrusion usually means that something, in this case a semi-solid paste that can be reshaped, gets pushed through a two-dimensional shape, known as a cross-section. You can see the cross-section there, that circular opening, reshapes the paste, and then the paste carries on in a direction that's normal to the plane that the cross-section was on, and it builds with the shape of that new cross-section. That's extrusion in a nutshell. Excuse me for a minute here. I need to go brush my teeth. And we're back. Industrially, a lot of important components are made using extrusion. Take this aluminum angle stock, for example. If you look really closely, you can see some scratches going along this lengthwise. Those little surface scratches are actually from this material traveling through a mold that has an L-shaped hole in it as a semi-solid paste before cooling into a solid in this angle shape, all while traveling normal to the plane of the die opening. Given an unlimited supply of aluminum, a piece could be made an unlimited length. It's the same idea as toothpaste, but it doesn't help oral hygiene one bit. So why are we talking about extrusion when we're talking about CAD? Well, we do it because SolidWorks makes a solid model by extruding a two-dimensional cross-sectional shape that's called a closed contour up off of the plane it was drawn on and through space. What this means is that any new part or feature is always starting as a two-dimensional drawing that sets the cross-sectional shape for this feature. This in turn means that any new feature starts as a two-dimensional drawing, and that to start any new feature, you must first tell SolidWorks what plane or planar surface you want to draw your sketch on. The sketch is the type of drawing that you do to create your two-dimensional cross-section. You can't write in air in real life. You need a surface to draw on. And that's the same for SolidWorks, except that while you can draw on a curved surface in real life, you always have to sketch on a flat plane in SolidWorks. If that's a little murky, don't worry. It'll become second nature pretty quickly when you start to do some drawing. Just remember, to start any new feature in SolidWorks, you always have to pick a plane to draw the sketch on before you can start to do any drawing. To understand how SolidWorks creates a virtual solid, think of a baseball bat moving through its arc. Even though it's not in every part of that space at every moment on its travel through its arc, it definitely occupies all of that space at some point during the swing. If you don't believe me, just go put your arm or some other part of your body within the arc of the baseball bat swing, and you'll see what I mean. The volume of the space that bat will occupy during its swing is a function of the cross-sectional shape of the outline of the bat and the path that it moves along. SolidWorks works in the same way. The CAD turns 2D into 3D by moving a cross-section off of its original plane and through space, and then turning all of the volume captured by that cross-section during this movement into a solid. The most common path that we'll ask the CAD to move our contours along is straight up from the drawing plane or straight down into it. Thus, we remember from a few minutes ago that this is normal to the plane, which is exactly why we covered the concept. It comes up a lot. This is called an extruded boss, base, or cut, which we'll come to again a bit later. To draw an extruded part, you can take a shape, and in this example we make a nice square here. We'll draw it on the XY plane. We then drag the shape through space along the Z axis, and because the shape here, the two-dimensional shape, closes in an area, as we move it off the plane it was drawn on and through space, it encloses and captures a volume. That's the most common way we make a 3D object in SolidWorks. We make a two-dimensional drawing into a three-dimensional virtual solid by moving it normal to the drawing plane. When we're going to laser cut something, where all we can actually do to make something is cut straight down through a material of finite thickness, every single part that we design will use this extruded method, this normal method, straight up and down. The laser cutter is kind of a combination between a James Bond bad guy weapon and a cookie cutter. When we make a solid in this way in the CAD, it's called, not surprisingly, an extruded boss base. We'll explain what the difference between a boss and a base is in a later lesson, but for now, just remember that a boss base always adds material when it moves a contour through space. The next type of shape we can make in SolidWorks again starts with a sketch drawn on one plane. So we start by picking our plane because the first thing we always have to do is tell the CAD where we want to draw our sketch. For this type of solid, we'll first need to set up a line called an axis, which will act like an axle. Things revolve around axles. Then we'll put a contour off to the side of that axis we've just created. Now we've got our nice shape here, and it captures the area within its contour. To make this into a solid, what we're going to do is we're going to swing it around the axis as though it's a tetherball. And like the baseball bat example a little earlier, every bit of volume that the tetherball would displace while revolving around the axis becomes part of the solid. In other words, where you don't want your head to be when the opponent serves the tetherball is where the solid, or cut, if it's a removable material, will appear. The contour will always stay the same distance from the axis, and we can choose how many degrees it travels through this arc. A 360-degree rotation through the arc would produce a round contour that creates my favorite shape, the donut. Contour, of course, doesn't need to be a circle. Any valid contour that encloses an area can be revolved around the axis to make a circular 3D version of itself. This feature tool is called the revolved boss base if it's being used to add material. If it's removing material, it's known as a revolved cut. So those are the two tools that we use to do a solid operation from a single plane. When we open the CAD, we'll find that those two tools will be lit up while all the other 3D tools will be grayed out. This is because we have to have sketches on more than one plane for any of the remaining types of 3D operations. If any of you are SpongeBob fans, the next 3D tool makes sense to you once I explain it, or you'll get really confused and I'm a really bad teacher. So here goes. If we think of SpongeBob when he's jellyfishing, the jellyfish are just kind of floating around in the water and they're pretty stationary other than bobbing up and down a little bit. Along comes Bob with his net and he runs through them, and he leaves behind a curvy tunnel of missing jellyfish. The cross-section of that tunnel is going to be the exact same shape as the opening of his net. The path of that tunnel is going to be the exact same path that SpongeBob ran along. SolidWorks will add or subtract material in the same way. To do it, we need two planes that intersect each other. On one plane, we draw the path that we want to move our contour along. On the other plane, we draw the cross-section, contour, that we want to move along this path. We then create a special relationship between the path and the contour called a pierce relationship, and we'll talk about that in later lessons. This action will move the shape so that it's touching the path where the path pierces the plane. Once we've done those actions in SolidWorks, we can then sweep the shape along the path, and it will capture the volume that's either to be added or removed from the solid material. In this case, because we're adding material, it would create this kind of spaghetti-like shape. This is, as we alluded to earlier, a swept boss base, and a swept cut if we're removing material like SpongeBob did. As you can see, there are two more ways that we can turn a two-dimensional drawing into a solid in SolidWorks. But the last one, which is called the boundary boss base, we don't actually use because it's just kind of a specialized version of the second last one. So one of the coolest things that we can do in terms of making shapes is to make a shape on one plane, make another shape on a different plane, and get SolidWorks to connect the two of them into a solid. This is very helpful when making more organic shapes. Shapes like a human arm don't tend to be made from perfect geometric shapes, and they don't tend to run in straight lines or perfect normals or parallel alignment. This tool will gradually change the cross-section from the contour of the first shape to the contour of the second shape as it fills in or removes the material between the two along the way. We can also set things up with guidelines so that we can make the transition from one contour to another follow a specific path. This tool is called the lofted boss base if we're adding material, and called, well, you guessed it, a lofted cut if we're removing material. You'll see a lot of real-life examples of lofted shapes in the construction of ships and aircraft. An aircraft fuselage is a series of cross-sectional shapes on different planes that set the shape of the fuselage as you go along the length. The wing has progressively changing contours, and the skin comes along and ties it all together and creates that very specific shape. The wing can be quite long front to back where it meets the fuselage, and then quite short in this direction at the tip. The bulkhead of a ship, which sets the cross-sectional shape of the ship at the longitudinal plane that it's located on, there's some big words for you, is another real-life example of lofting. So, that's the main 4 ways that we will use to create a solid from a 2D sketch. Unfortunately, there are some problems that can crop up and cause errors, so we're going to cover them now so that you don't get confused if they come up while you're doing a drawing later on. So if we look at them now, we can try to avoid them, or at least find them and fix them. If you were listening carefully to what I was saying earlier on, you would have heard me very specifically choosing the words closed contour time and again. The first 2 types of sketching errors that are going to trigger an error message when you try to do a 3D operation are both caused by the sketch not being a closed contour. If the entire sketch is not a closed contour, it won't capture an area, which means that when we move it off the plane it's drawn on and we start to drag it through space, it won't capture a volume. Any valid 3D object has to have a volume. If it doesn't have a volume, it's not 3D. This type of failure, the failure to create a finite volume, applies whether the entire contour has a problem or just part of the contour has this problem. The first version of this type of failure that we're going to cover is when we've got a square or any other shape and we haven't quite closed it up. If we think of this as an area, well, we haven't enclosed that area. If this was a sheep pen, the sheep could sneak out and run away here and do whatever sheep do when they get out of the pen. The non-farming problem here is that when we extrude that shape along the z-axis, because it didn't capture an area in 2 dimensions, it won't capture a volume in 3D. The error message that will come up will be called an open contour. So if you get the open contour error instead of a nice translucent yellow 3-dimensional part preview when you go to do your 3-dimensional operations, what you're looking to fix is a little opening where the lines just aren't quite connected. This problem tends to come up when you're manually setting a shape in sketch mode. You click to start a line, click to finish line, click to start a line, click to finish line, click to start a line, click to finish the final line, but you haven't quite got that final line connected. You think you do, but you don't. That's the most common cause of the open contour error. The next type of error we're going to talk about is also a problem where part of the drawing does not have a volume when extruded. It's also the error with the funniest name. In this case, we've got our square, but it's got an extra line hanging off it here. We've got our closed contour. It's nice, it's closed, it's not the prettiest square ever, but it does capture an area. But then when we sweep this along the z-axis, we get this shape. Right, we get our cube, it's fine, but we also get this little wall hanging off here. It doesn't have a finite thickness because it's just made up from a line. So it's not a closed shape of any sort, and it can't be a volume. It's just a 2-dimensional wall hanging off a cube, meaning that it is not a valid 3D object and the whole sketch will fail to extrude, revolve, sweep, or lock. You'll get an error message saying that your sketch contains a dangling entity. So, when you get the dangling entity error, what you're looking for is an extraneous line that hangs off your contour sketch. We call this the click-happy error because it tends to come up when, like the open contour error, people are manually setting up a contour shape. But in this case, instead of missing the connection to the last point, they double-click to end their line instead of single-clicking. This immediately starts another line. The person then clicks again to stop drawing this and thinks everything is fine. But they've managed to leave a little tiny line hanging off the end of their drawing. This line could be 1/100th of a millimeter long, but if it's there, you're not going to get a proper extrusion. So, when you get the dangling entity error, it's probably from overclicking. To find the problem, look for a little extra line that's not part of any closed 2D contour. To fix the problem, you simply delete the extraneous line. Okay, so that covers the two volume-related errors that can come up. The remaining two errors have to do with trying to share a line or a point between two different solid objects. In the first case, we've got, say, a closed X shape like this. Everything should be fine. That's a valid closed contour. This is a valid closed contour too. Then we extrude it along the Z-axis. We get this kind of squared off hourglass looking thing. Does this vertex belong to this solid or this solid? The answer is that we don't know, and neither does SolidWorks. Mathematically, if it belongs to one solid, then the other is missing a vertex, which is not good. If it's two separate pieces, no matter how small this gap is, we're good to go. If it's like this, and there's a little opening so that this line is continuous, it's a continuous contour, and that's also okay. To fix this, if we really do want this shape, what we can do is, instead of asking the CAD to extrude the entire thing at once, we can select this contour, and then select this contour separately. Then the CAD will kick into a mode where the mathematics can actually handle this situation. If it wasn't intended that the lines of the sketch would crisscross themselves, the other solution is to simply redo the sketch and avoid crisscrossing lines. This error is called a self-intersecting contour. Where it's very common is when you're extruding fonts. Right, so we can have a letter and that's fine. No self-intersecting contours here, but a lot of cursive letters will cross themselves or they will cross over the next letter, and that will cause the self-intersecting contours. What's a little more subtle is that you could have a letter that looks like the world's most perfect letter, but if you zoom in, you find that the line work is actually a big mess. What looks like a nice straight line is kind of a rat's nest. So what happened there? Well, some fonts are made up from hand-drawn fonts that were scanned in. When you scan something in, it picks up a series of points called rasters, and then it puts it through a vectorizing software, which ties all the points together with a series of straight lines. Doesn't always get them in a linear fashion, and that's where you can get this messy line work. These can be fixed if you've got a font that you really like, but it's very time-consuming. The last type of error we're going to run into is a situation that's very similar to the self-intersecting contour, except that in this case, instead of sharing a point, two contours are sharing a line, or a single contour has two lines right on top of one another. You've got, say, a contour here like this, and you've got a contour here like this. The problem will be this line. When you extrude the drawing, the CAD won't know whether to attach this face to this volume or to this volume. The solution is the exact same as before. You can separately pick this one and then this one instead of having the CAD try to extrude them all at once. This will kick in the math that allows the CAD to handle the situation. Or you can simply draw them separately if that's what you really intended to do in the first place. The name of this type of error? It's called an endpoint wrongly shared by multiple entities. The most common cause of this error isn't actually drawing two boxes right beside each other. It's actually when you've got a situation where you've drawn a box, but you had drawn a reference line earlier on, and that reference line is buried under one of the lines in your contour. You forget to delete it, and now you've got a double line. So this endpoint here is wrongly shared by a non-extrudable line and an extrudable contour. So that covers the 4 reasons that the CAD will fail to convert a sketch into a valid solid. This also covers the 4 ways that we can use to get the CAD to make a 3-dimensional solid model from a 2-dimensional sketch. Now that we have this basic knowledge in hand, we can actually proceed to the software and begin to learn how to operate it. Thanks, and we'll see you again in Lesson 2.